Welcome back everybody. I am a teacher from Ilm Online Academy. In today's video, the topic is reactivity of the metals. This is basically chapter number 15 of the ongoing series for the Cambridge Chemistry 0620, and in today's video we will be having a look at the reactivity of the metals. So the contents which we will discuss today are: first we'll talk about the reactivity series of the metals, and second we'll talk about the displacement reactions of the metals. Without further ado, let's just begin, and let's first start with the reactivity and the reactivity series. So this one you can see here we have the reactivity and the reactivity series. The most basic definition of the reactivity is the ease with which a chemical substance take part in a chemical reaction. And as we know that most of the elements in our periodic table are the metals, and most of them are very useful for a wide variety of different purposes, like as we have also read in the previous chapter, the uses of most of the metals like iron, copper, zinc, and iron has an enormous number of uses. So that's why we have this reactivity and the reactivity series, which we will discuss today. And in the group 1 of the periodic table, in chapter number 13, we have read about that how reactivity changes in a particular group. Group 1 and group 2 are highly reactive, right? And group 8, or you can say that the group 0, which is the last group, is unreactive, which contain the noble gases. So we also refer to the fact that the transition metals are less reactive than the metals in the group 1 and the group 2. Many of the important metals that we use in different ways come from more than one group, and here the question rises whether there is a broader order of reactivity series which includes all the metals. So according to that, we will look at the reactions also which allow us to place the metals precisely in a series and consider the reasons for the order that we observe. So in the reactivity series, this is the order of reactivity of the metals, giving the most reactive metal first, and based on the result from a wide range of experiments involving metals reacting with the oxygen, water, hydrochloric acid, dilute hydrochloric acid, and mostly we have the metal salt solution reactions, which we also discuss in detail in today's video, and also the displacement reactions of the different metals. So based upon all these experiments, we have a reactivity series. It is you can say that it is basically just because of these reactions we place the metals precisely in a series and consider the reasons for the order we have. So this is about the reactivity and the reactivity series. As we know that metals tend to readily lose the electrons and they form the cations. Like metals have the property to form the cations because they have free electrons. Because of those free electrons, they can easily lose them and form cations. Most of them react with also the atmospheric nitrogen, and when metals react with the nitrogen, we have also read this general equation: metals plus oxygen. After reaction, we have metal oxides. When oxygen react with any substance, oxide is formed, like carbon monoxide, carbon dioxide. However, different metals have different reactivity towards the oxygen. Unreactive metals like we have gold, platinum, which we also discuss in the chapter number 14, they do not readily form the oxides when they are exposed to the air. So those are considered as the unreactive metals. But some are highly reactive or most reactive, like potassium, sodium, calcium. These are considered as the highly reactive metals. So this is about the reactivity of the metals. Now I will show you here the reactivity series of the metals which was prepared. So this one you can see here, this is the reactivity series of the metals of our periodic table. So after the introduction of this reactivity series, I will discuss with you the reactions of the or experiments, different range of experiments that involves the metals reacting with oxygen, water, acid, through which we have a basis to make this reactivity series. So This reactivity series, the metals at the top of the reactivity series are powerful, they are strong, you can say that they are powerful, and they are reactive. Like we have the metals here, sodium, potassium, lithium. These metals are highly reactive, you can say that, which are present at the top, and they are also the powerful reducing agents. We have also read about in chapter number 10 about the oxidizing agents and reducing agents. Reducing agents are those which help others to reduce, and they oxidize itself. Since they are highly oxidized, so these metals easily corrode away, and the reducing ability of the metals grows weaker while traversing down the series. Like if we move down the series, then the reducing agent or the reducing property of the metal decreases. And next, all the metals that are found above the hydrogen in this reactivity series, like here above hydrogen we have in this reactivity series, they give us hydrogen gas when upon reacting with acid or H2SO4. Like from potassium to the lead, when these metals react with the acid, or when they react with dilute hydrochloric acid or dilute sulfuric acid, they liberate hydrogen gas because they are much reactive than the hydrogen. Hydrogen is not a metal. Hydrogen is a non-metal, but it is only included for the comparison in this reactivity series. We also have we can also put the carbon in this reactivity series just for the comparison, but both are not metals. So for doing the experiments with the hydrogen, or for doing the experiments in the presence of dilute acids, you can use hydrogen for the reactivity series, or just for telling the reactivity series of the different elements. So the elements that are present above the hydrogen in our reactivity series, they are highly reactive, and they can liberate hydrogen gas when they react with the dilute acid like sulfuric acid or hydrochloric acid. Metals that are placed higher on the reactivity series have the ability to displace the metals that are placed lower from their solutions. Like for example, we have potassium nitrate plus we have, suppose next will be, we have calcium chloride. When both of these react together, what will happen? As we know that potassium is much more powerful as compared to the calcium, so potassium can easily displace calcium in the calcium chloride, and it will form potassium chloride. So the metals that are placed higher on the reactivity series, they have the ability to displace the metals that are placed lower. So for example, another example is sodium. Sodium can easily replace iron. Lithium can easily replace iron. Barium, strontium, calcium, all that are present above the iron, they can easily displace the iron in the reactions. High ranking metals require great amount of energy for their isolation from their ores and also from the other compounds. So this one is the reactivity series of the metals. We will also talk about the reactions of the metals with water, with acids, with air, oxygen, and you can see here on the top we have the metals which are more reactive, and the metals which are present at the bottom of the reactivity series, these are unreactive or least reactive. So reactivity series arrange the metal in order of their reactivity. This can be used to predict the product from the reactions. Non-metals, hydrogen and carbon are often included in the reactivity series just for the comparison of the metals, or we can check the displacement reaction by these. Hydrogen is present here below the lead, and we can also place the carbon in the reactivity series. The placement of the carbon will be below the aluminum. We can place the carbon below the aluminum, and this can be useful this carbon, which we are including in the reactivity series, is useful for the extraction of the metals, which we will discuss in the next chapter. We can extract the metal from their ores by using carbon. Reduction with the carbon, we have an important reaction of that, which is reduction with the carbon. So we can check that which metals can be easily replaced with the carbon or which are not. So the metals that are present above the carbon cannot replace them, but the metals that are present below the carbon can easily replace them. So we can use, or we can reduce them with the carbon. So this is about the reactivity series. Next, I have some important frequently or some important questions which are related to the reactivity series, or which can also be asked in the exam. First, what is metal reactivity? So you can see here, reactivity series is a list of metals that are arranged in the decreasing order of their reactivity. The top are the most reactive and bottom are least reactive, and for any two metals in the series, the metal placed higher in the series can displace the metals which are present at the lower. Like calcium. Calcium is more reactive than the lead, so calcium can easily replace the lead in any reaction. That is the displacement reaction. We will also discuss about detail in the displacement reaction. Second one is, why is hydrogen placed in the reactivity series of the metals hydrogen and also carbon? As I already told you, this is only for the comparison, or we can also use this one for the extraction of the metal from their ore. So hydrogen is part of the reactivity series of the metal because hydrogen has both the properties. We have also discussed the properties of hydrogen in our previous chapter. Hydrogen can form H positive and also H negative ions, right? So when hydrogen loses an electron, it forms H positive ions. So this is the property of the metals, that they form the cation or the positive ion. That's why we are placing the hydrogen in the reactivity series. Next, what is the significance of the reactivity series of the metal? The reactivity series of the metal is just the area of the metals in the descending order of their reactivities. It will help us to predict if a metal can displace another metal in a displacement reaction or not. Like potassium is present on the top, and potassium is more reactive as compared to the aluminum. So potassium can easily replace the aluminum in any solution or in any salt, in any compound, in anything, because potassium has more reactivity. So just because of its more reactivity, potassium can easily replace the aluminum in any compound. How is the reactivity series of the metals originated? Reactivity series of a metal is originated from a range of experiments with oxygen, which dilute hydrochloric acids, with air, water. So in the activity series or reactivity series of the metals, more reactive metal is placed in the top of the series by doing or by experimenting a range of so many experiments with the metals, and less reactive metals are placed at the bottom. We have less reactive metal like gold, platinum, which we also use for the jewelry, for ornaments, right? For jewelry purposes, you can use the gold, platinum, silver, because it does not react with the water, not with the air, nor with the oxygen or anything like that, because it's least reactive. So that's why you can easily wear them anywhere, anytime. So these are the most frequently asked questions related to the reactivity series. So next, we will discuss about the reactions of the metals. First, we will talk about the reactions with the water. So here we will talk about the reactions with the water. We will describe the reactions, if any, will occur of potassium, sodium, calcium with the cold water, and with steam, magnesium, zinc, iron, copper, silver, and gold with the dilute hydrochloric acid. And we'll also explain these reactions in terms of the position of the metals in the reactivity series. So first of all, we will talk about the reactions of the metals with the cold water, the reactive metals with the cold water, and the reactive metals which are included in our product in our reactivity series. These are potassium, sodium, and suppose third one is calcium. So we'll see the reaction of these reactive metals with the cold water. we have a cold water and we have a steam. So first we'll check the reactions of these metals with the cold water. When potassium reacts with the cold water, potassium melts and floats, moving rapidly on the surface, and what will happen, a lilac flame will be produced in case of the reaction of potassium with the cold water, and will also ignite, and sometimes at the end of this reaction a small explosion will occur also. A small explosion occur also of the reaction of this one. Potassium will have the most violent and most vigorous reaction with the cold water, since it is at the top of the reactivity series. As you can see here, potassium is present here at the top. So why we place it at the top of the reactivity series? Because it is highly reactive. So a lilac flame will also ignite. Sometimes in the reaction a small explosion will occur, and at the end of the reaction we have the most violent and the most vigorous reaction will be seen in case of potassium with the cold water, because it is present at the top of the reactivity series. The one which are present at the lower will have much less reaction as compared to the potassium, because potassium is present at the top. So this is the reaction of the potassium with the water, and what will happen, we have some equation also, journal equation. First I will write journal equation: potassium plus water. Any metal when reacts with the water, it produces potassium hydroxide, KOH, plus we have hydrogen gas that is released. So I think I should write here H2O, that will be much better. So like this. So when potassium reacts with the water, what will happen, we have potassium hydroxide and hydrogen gas is released. So this reaction is not balanced, so we will balance out this equation first. As we should put 2 here, 2 here also, and 2 before the QS. So now this reaction is balanced. So this is the reaction of the potassium with the cold water. What will happen, as potassium is highly reactive, you can see here potassium is present above the hydrogen, right? So potassium is more reactive than the hydrogen. Potassium can easily replace the hydrogen in any compound, in any solution, in any salt. So here we know that water contains 2 types of ions. We have hydrogen ions and we have hydroxide ions in the water. So potassium is a cation, so it can easily replace the hydrogen in the water, and it will react with the hydroxide ions that are present in the water, and when it reacts with this forms potassium hydroxide, or metal hydroxide is found, plus hydrogen gas is released. So this is the equation for the reaction of the potassium with the cold water. Next we will talk about sodium, and then we'll talk about the calcium also separately. So the second one is sodium with the cold water. So when sodium reacts with the water, the metal melts to form a ball that moves rapidly around the surface. The ball fizzles rapidly before it disappears, but the reaction of the sodium and water is less vigorous as compared to the reaction of potassium with the water. Why? Because potassium is present at the top. So potassium will have the most vigorous and most violent reaction from all the metals that are present, because potassium is present at the top and all the metals are present at the lower than the potassium. So we have the equation of the metal of sodium with the cold water. So first we have the word equation: sodium that reacts with the water and it forms sodium hydroxide, plus we have hydrogen gas that is released, plus H2. What will happen here? How we can say that the reaction is progressed or the reaction happens? You can You can easily check the reaction just by the we can say that if hydrogen gas is released or bubbles are produced, because sodium is solid that we are using here as a solid sodium, and you know that water is present in the liquid state. So when sodium solid is added into the water which is present in the liquid state, bubbles will be produced, and those bubbles are of the gas that is produced in that reaction. And it is obvious that the gas that is produced here in this reaction is hydrogen gas, right? Because sodium will react with the hydroxide ion. Sodium is a cation, Na positive. It forms the cations, and cation attracts the anion, right? So sodium hydroxide will be released with the production of the gas, and that gas is hydrogen gas that is released here. So when bubbles are produced in the solution in the liquid of water, you can easily predict that the solution the reaction goes on, and we have the products now which is the gas, hydrogen gas, and we have sodium hydroxide, that is the product. So what will happen when a gas is produced? It forms the bubbles in the solution, and bubbles will rise to the top because gases always move upward, right? So this is the equation how sodium reacts with the water, and it forms the sodium hydroxide plus we have hydrogen gas. So now we have third most reactive metal, which is the third metal which is included in the highly reactive metals. From the top we have sodium, potassium and calcium. These are included in the most or highly reactive metals of the reactivity series. So we'll see here calcium. When calcium is added to the water, the reaction is slower as compared to the sodium and the potassium, and it is less violent. Why it is less violent? Because potassium is present below the sodium and the potassium in the reactivity series. So that's why the reaction of calcium is less violent as compared to the potassium and the sodium. But if we compare the reaction of calcium with the aluminum and manganese, then calcium is much more violent, because aluminum has less reactivity as compared to the calcium, and manganese and zinc also has less reactivity. So that's why calcium has much more highly vigorous reaction as compared to the aluminum and zinc. But if we compare it with the sodium and the potassium, which are most reactive or highly reactive, so then that with the comparison we have less violent reaction than the reactions we have done here. So the calcium metal sinks in the water, and after an hour or so, bubbles of hydrogen gas can be seen on the surface of the metal. When bubbles are produced, this is the indication that we have now the reaction has done now and products are produced. So calcium will have a less vigorous and slower reaction with the cold water, since it is present lower than the sodium and the potassium in the reactivity series. So we have the word equation and the symbol equation of calcium with the water, cold water. Calcium, when it reacts with the water, calcium plus water, after reaction we have calcium hydroxide plus hydrogen. This one is the word equation. Next I will also write the symbol equation. We have calcium that is present in the solid state, plus most of the metals are solid, most of the metals, not all, most, and water that is present in the liquid state. When we add the calcium in the liquid water, we have calcium hydroxide, that is also known as slaked lime, plus we have hydrogen gas that is released. When the bubbles are produced, then this is an indication that the reaction has gone to the completion. So this is how the highly reactive metals of our reactivity series react with the cold water. Next we will talk about the reaction of these metals with the steam. Before moving towards the reaction with the steam, I will show you of the reactions of the group 1 metals with the water, or I will tell you also the trend in the group. For example, if we have group 1, right? We have group 1 of our periodic table. Group 1 contains lithium, we have sodium, we have potassium, lithium, sodium, potassium, rubidium, cesium, francium, all are included in the group 1. So if we move, or if we check the reaction with the water, what will happen? If we move downward from top to the bottom, what will happen? We have increased reactivity, or reactivity is increasing if we move from top to the bottom. Why? It has so many reasons. Just because of the one reason is also that the size increases, the electrons that are present in that, we have more electrons as we move from top to the bottom. So the shield of the nucleus, or nucleus attract those electrons not much stronger as compared to the above. Lithium has just 3 electrons, so nucleus has a stronger effect or stronger attraction to the electron, but sodium has 11 electron, so the last electron will not more attracted or more strongly attracted to the nucleus than as compared to the inner electron. So that's why you can say that increasing reactivity from top to the bottom. As we have also observed that in the reactivity series, potassium is present in the top, right? So we have this, the reactivity series of the group 1. Next, if we talk about the group 2 metals, which also show the similar trends in the reactivity to the group 1, but they are less reactive than the metals in the group 1. So reactivity in case of, if we have group 2 are the alkaline earth metals. We have calcium, magnesium, these are included in the group 2. So again, reactivity increases going down the group. If we move down the group, then reactivity is increases. So reactivity increases in group 2 also. Magnesium react very slowly when placed in a cold water. Bubbles of hydrogen form very slowly on the magnesium ribbon. A much stronger reaction is obtained if the steam is passed with the metal or over the heated magnesium. So we have the reaction, or you can say that the group 1 metal show the reactions more strongly with the cold water, not the group 2 metals, because they have not much as reactivity as compared to the group 1, but they show a vigorous reaction when a steam is used. So when magnesium that is present in the group 2, when magnesium react with the steam, we have magnesium that is present in the solid state, plus we have steam H2O. In the previous reaction we took the water in the liquid state, but now here as a steam, so you can use here as the gaseous state. So when magnesium reacts with the water, it forms magnesium oxide MgO, plus we have hydrogen that is released. So hydrogen gas is released in this. The magnesium glow brightly to form the hydrogen and the magnesium oxide. So this is the reaction of how magnesium reacts with the water. So we have also calcium. Calcium also reacts strongly with the cold water, as we have done this before. Calcium hydroxide here that is formed here is more soluble as compared to the magnesium hydroxide, which so an alkaline solution is produced. As the reaction proceeds, white suspension is obtained, but not all the calcium hydroxide dissolves. So moderately reactive transition metals like zinc, iron will also react with the steam in a similar way, just like magnesium reacts. Other transition metals like copper, silver, gold do not react with either the water or the steam because they are less reactive metals, right? So based upon the reactions we have seen so far, we can put the metals considered in the order of their reactivity series. Like, we can place the metals of, we have potassium here, potassium on the top, and then we have sodium, and then we have calcium, we have magnesium, zinc, iron, copper, silver, and then we have gold. So here these are the metals which we discussed up till now. So most reactive are present here. The most reactive one we have most reactive here. Potassium is more reactive. Then we have sodium, and then calcium, magnesium, zinc, iron, copper, silver, and then gold. So this is how the reactivity of the metals, most reactive on the left and least reactive on the right. So these are the reactions of the metals with the water. Next we will talk about the reactions with the dilute acids. So the reactions with the dilute acids, like dilute hydrochloric acid mostly that is used, we have the metals that are present in the top of the reactivity series as potassium, sodium and calcium. As they are too reactive, so the reactions with the hydrochloric acid are too dangerous to be attempted if we are using the dilute one also. So further down the reactivity series, the slower the reaction until no reaction will occur, and only the metals above the hydrogen, like here you can see this is the hydrogen, so the metals that are present above the hydrogen in the reactivity series will react with the dilute acids, not the lower one. Lower one are highly unreactive, as you can see here, this one. So now we'll check the reactions of the dilute acids with the metals. Alkali metals of the group 1. Alkali metals of the group 1 and indeed the calcium are too reactive to safely add to even dilute acids. They do produce hydrogen but too vigorously. But we have some metals that also show the reactivity with dilute acids, and we have those metals like we have magnesium, metal. Magnesium, we have a strong reaction of magnesium with the dilute hydrochloric acid or dilute sulfuric acid. Bubbles of the gas will produce, magnesium disappears, colorless solution will be formed, and the equation for this reaction will be, we have magnesium when react with the dilute hydrochloric acid that is present in the aqueous solution. When they react, they form magnesium chloride, MgCl2 plus hydrogen gas is released. And when magnesium reacts with the sulfuric acid or dilute sulfuric acid, that is also present here in the aqueous form because it is diluted. So after reaction, we have magnesium sulfate plus hydrogen gases released. So this is we have the bubbles of the gas that will produce bubbles of the hydrogen gas, and magnesium disappears after that reaction because all the magnesium is converted into the magnesium chloride or magnesium sulfate in the respective reaction, and the solution will be, colorless solution will be formed in that case. If we talk about aluminum also reacts with the acids, but it's slow. Why? Because aluminum is present in the center of our reactivity series, and it has a moderate reactivity. It will react slowly. So we have from the top, if the top metals or the highly reactive metals react, it will be too dangerous. So we took the metals that are present below the highly reactive one. We took the magnesium. We have the aluminum. Aluminum will slowly react in the cold, but bubbles form on heating, and aluminum disappears, and colorless solution will be produced here. So when aluminum react with the hydrochloric acid, and this is also dilute hydrochloric acid, so when it reacts, they form aluminum chloride, AlCl3, plus we have hydrogen gas. This reaction is not balanced, this equation, so we will balance this out. We have 2 aluminum, we can take 6 here, 2 will be here, and 3 hydrogen gas molecules will be released in this reaction. Aluminum also reacts with the dilute sulfuric acid in the same way, but we have a different product will be produced, like aluminum sulfate will be produced here. Zinc, next we have zinc also form the bubbles. Iron, same iron and zinc, bubbles of the gas will be produced, and we have colorless solution in case of zinc, and we have pale green solution in case of the reaction with the iron. But in case of reaction with the dilute acids with copper, if we take the reaction copper, we have silver, and we have gold. These three metals, as these are highly unreactive metals of our reactivity series, so they show no reaction with the dilute acids. They showed no reaction, right? So why they show no reaction? Because they are highly unreactive. So that's why we have this reactivity series of the reaction. We have the we can also generate a journal equation for the reaction with the acids, like we have a metal. From the above reactions, you can summarize a journal equation, metal plus acid, and when it reacts, they form a metal salt like magnesium chloride, like magnesium sulfate. So a metal salt is produced, plus we have hydrogen gas that is released. So this one is the journal equation. By remembering this one, you can easily do for any metal. You just have to place any metal in this equation and acid which you want to use, like hydrochloric acid, sulfuric acid, any other. So the reaction of the metal with the dilute acids, that can be carried out, and we can confirm the reactivity which is seen above. We have done the experiments with magnesium, aluminum, copper, silver, and gold. So based upon these reactions, you can have the reactivity series, like we have magnesium, highly reactive, and then we have zinc. We have, before zinc we have to add the aluminum. We have aluminum, we have zinc, then we have copper, silver, and then we have gold. So this is the reactivity order of reactivity based upon the reaction with the dilute acids. Magnesium is the most highly reactive, and copper and gold and silver are the least reactive. So you can see that aluminum reacts less strongly. That would be expected. This occurs because aluminum reacts easily with the oxygen in the air to form Al2O3, that is the aluminum oxide, that resists the corrosion also, which we have also done in the previous chapter, how aluminum forms a protective layer, or layer of oxide is formed above the metal, which will protect the underlying metal that is present in it. So we have the reaction of the metal with the water and acids that allow us to place the hydrogen in the reactivity series, even though it's not a metal. So this is useful as it demonstrates that the metals higher in the reactivity series are more reactive than the hydrogen, and they can displace the gas from the water or acids under the appropriate conditions, as which we have done here. So we can place the hydrogen above the copper or below the metals like zinc and iron. So potassium, sodium, calcium, magnesium, aluminum, zinc, these can easily replace the hydrogen, like in these reactions. Like aluminum can replace the hydrogen in the hydrochloric acid, and it will react with the chloride. So that's why there is a reason why we put the hydrogen is a non-metal, right? But we put in this reactivity series that belongs to the metal. So why? That is the basic reason behind it. So we are done with the reactions with the dilute hydrochloric acid. Next, dilute hydrochloric acid and dilute sulfuric acid. So next we will talk about the metal displacement reactions. These are most important ones. So we have the displacement reactions. A reaction in which a more reactive metal displaces a less reactive metal from the solution of its salt. A displacement reaction can help us to place the particular metals more precisely in the reactivity series. We can use this type of reactions to compare directly the reactivity of the two metals. Like in a displacement reaction, a more reactive metal displaces a less reactive metal from the solution of its salt. And in this type of reactions, we have two metals that are in direct competition with each other. Like if a piece of zinc is left to stand in a solution of copper sulfate, then the reaction will occur, and that reaction will be, we have a piece of zinc metal that will react with the copper sulfate, CuSO4. Now we have two metals from our reactivity series, as you can see here, zinc and copper. So when zinc reacts with the copper sulfate, what will happen? Now we have to check the reactivity of the metals from our periodic table, from our reactivity series. We have two metals. We have zinc in the reaction and we have copper. So you have to check the reactivity where they are placed in the reactivity series. Zinc is present here. We have zinc here and we have copper here. So you can easily see that, or you can easily check that zinc is more reactive as compared to the copper because zinc is present above the copper, right? So zinc can easily displace copper in this reaction because displacement reactions, in the displacement reaction, the two metals are in direct competition, and the one which is more reactive displaces a less reactive metal from the solution of its salt. So zinc will replace the copper, but copper will not. So in this reaction, what will happen? We have zinc that is present in gray color, and we have copper sulfate solution which is blue. Copper sulfate is the solution, aqueous solution. So when it reacts, it forms zinc sulfate. Zinc can replace the copper because zinc is more reactive, plus copper will be present there as a metal. We have a colorless solution of the zinc sulfate, and copper is present in the red brown color. The red brown color of copper will be seen here in this reaction, so you can easily say that the copper is produced. The observed effect of the reaction is that the zinc metal becomes coated with the red brown layer of the copper, and the blue color of the solution fades away and it becomes colorless. The solution eventually becomes colorless because of the zinc sulfate. Zinc disappears the copper from the solution, so zinc is more reactive than the copper. Zinc is more reactive than the copper, and it can easily displace the copper from the copper sulfate solution. But if we talk about the reverse of this reaction, like copper plus zinc sulfate, no reaction. Why no reaction? Because zinc is more reactive and copper is less reactive, so copper will not replace the zinc or will not displace the zinc in the zinc sulfate. The reverse reaction does not happen. A piece of copper does not react with the zinc sulfate solution. Copper is an unreactive metal when tested in the various ways. So there are some metals that are even less reactive. Silver is a metal that is less reactive than the copper. If copper metal is placed in a solution of silver nitrate, then a solution does occur. Like we have silver nitrate solution AgNO3, plus we have a copper metal. So when it reacts together, the solution becomes blue just because of the formation of the copper nitrate solution. We have copper nitrate. Copper can replace the silver in the silver nitrate, plus we have silver here. So 2 will be placed here and 2 should be here, like this. So a deposit of the silver grows on the surface of the copper. The solution becomes blue because of the formation of the copper sulfate solution, copper nitrate solution, sorry. So how this happens? Just because of that, copper is more reactive than the silver, so that's why copper can displace the silver in this reaction. But if we talk about the reaction of the copper with the zinc sulfate, it does not happen because zinc is more reactive. But if we talk about the reverse, like silver will be replaced here, like the reverse of this reaction here, this will not. Why this will not? Because silver is less reactive than the copper. So copper displaces the silver from the solution. Copper is more reactive. The reaction has been used to produce the silver pine tree by using a silver nitrate. But the reverse of this reaction will not happen. So we have these displacement reactions, and next we'll talk about the displacement reactions as a redox reaction. So displacement as a redox reaction. We have read about the redox reaction in chapter number 10 of this one. You can check the detail about the redox reactions from the chapter 10 video. Reactive metals, as we have also discussed before, reactive metals are good reducing agents. Reactive metals that are present there in the reactivity series, that are present on the top, or you can say that which are present on the top of the reactivity series, those reactive metals are good reducing agents, and reducing agents are those that help to reduce others and they oxidize itself. So those are the reducing agents, and they lose the electrons. The most reactive metals are those that can lose electrons most easily. So reactive metals are those most readily to form the positive ions. And you also remember from chapter number 10, oil rig, right? I think you remember the oil rig mnemonic which I told you in the chapter number 10. Oxidation is the loss of electron and reduction is the gain of electron. Oxidation, loss of electron, reduction is the gain of electron. So we have a nature of reaction that take place between the zinc and the copper sulfate, and that can be explored in more detail by looking at the ionic equation for this reaction. Like we have zinc plus we have copper ions. Because why we have copper ions? Because we have the copper sulfate solution. So in that solution we have the copper ions, and when it reacts together they form the zinc ions Zn plus 2, plus we have the copper that is in the stabilized form. This shows that the reaction is a redox reaction, and it involves the transfer of 2 electrons from the zinc atoms to the copper. What will happen here? Zinc is stable or zinc is neutral before the reaction, but when the reaction happens, zinc loses 2 electrons and it gives those 2 electrons to the copper. So zinc atoms are oxidized because oxidation is a loss of electrons. So zinc are oxidized here. You can see that. And copper ions are reduced. Copper is reduced, copper gain that electrons, right? So in general the atoms of the more reactive metal lose electrons to become the positive ions, right? Like we have zinc as the more reactive, so zinc will become the ion, it loses the electron, and we have also some, and it gives those electrons to, those 2 electrons are donated to the metal which is less reactive. So more reactive metals are give more electrons, or you can say that lose electrons to become the positive ions. So we have the copper ions take that electrons to become the copper solid metal. So we have some reducing agents like which zinc. The important features related to the reducing agent, like zinc loses the electron as you can see here, and second we have zinc is oxidized here, right? So the more reactive metals will do the same like the zinc, and oxidation number increases. You can see here oxidation number of the zinc increases. For the reaction it's 0, but after the reaction it's plus 2. So oxidation number increases. So these are the properties of the reducing agents. So based upon these redox reactions, reducing agent is the zinc, and we have the oxidizing agent that is the copper. Copper gained the electron from the zinc and it reduced. So other one is oxidation number decreases. There is a decrease in the oxidation number from plus 2 to the 0. So that's why based upon these redox reactions you can also write the half equations of this one, in which zinc, which is a more reactive one, loses the electron and form the ion as a zinc ion, right? So we can also write the half equation of the copper, right? So the metal displaces the hydrogen from the water also, or an acid, that is also the redox reactions, and the reactive metal from the positive ion during the reaction, and the hydrogen ions in the water or the acid gain the electrons and so are reduced. Consideration of these reactions with the water and acids at the redox reactions, we can give the justification to the inclusion of the hydrogen in the reactivity series even if it's not a metal. So displacement reaction in the solution help us to compare directly the reactivity of the two metals and to establish the order of reactivity in the reaction also. So this is about the reactivity of the metals and the displacement reactions. Next, I will just give you an overview of the metal reactivity, like just an overview of the reactivity of the metals. The reactivity of the metal, like we have, by using specific metal displacement reactions, we have done the reactions of the metals with the water, with the cold water, with steam, with oxygen. So we can clear about the order of the metals in the sequence. The reaction of the metals with the water and acids also help us to place the hydrogen into sequence, even though it's not a metal. And information on the reactivity of the metals has been found from the various aspects of the chemistry also, like the reaction with the air. We have reaction with air or oxygen, reaction with the water, and next reaction with the dilute acids, and next in the last we have displacement reactions also. So just based upon these overall reaction that emerges, that is known as the reactivity series, and the evidence for the position of the carbon comes from the method which we use to extract a metal, which we will discuss in chapter number 16. And carbon is also placed between the aluminum and the zinc, because it can reduce the zinc oxide to form the zinc, but cannot reduce the aluminum oxide. So the reactivity series, which I already show you above, we have potassium at the top, and then sodium, and then we have calcium, we have magnesium, we have aluminum. You can place the carbon here below the aluminum, zinc, iron, and then you can place the hydrogen here. Above the hydrogen we have copper, we have silver, and we have gold. So these are the metals that are present in our reactivity series. We have done with the reactions of these metals. The top one are highly reactive, right? These are highly reactive metals of our reactivity series. So reactivity increases if we go from bottom to the top. Reactivity increases. Potassium is the most reactive, and silver, gold, and copper are considered as the least reactive. We can also see from the redox reaction that most reactive metals are those that most readily lose the electron to form the positive ions, and the most reactive metals are the most powerful reducing agents, giving the electrons to other ions or also the compounds. So we have done with this one. Metals show the different levels of the reactivity and can be arranged in the reactivity series, and then we have different levels of reactivity that can be seen in the way of different metals react with water, with dilute acids, with oxygen. We have the elements of the group 1 also, which are the most reactive metals, which are present at the top of the series. Transition metals are moderately reactive, and then we talk about the metal displacement reaction that provide the evidence that help to bring us in detail the reactions of different metals with the metals. Next, we have a more reactive metal will displace a less reactive metal from the solution of the salt. Next, we talk about the position of the metal in the reactivity series that is related to the tendency of the metal to form the positive ion in the reaction. And in the last, we talk about the metal displacement reactions are redox reactions, and how they are redox reactions we talk about in detail in this one. So this one you can see here, this is the table that summarizes all the reactions which we have done before. The reactions of the metals of our reactivity series here. from potassium to the gold, and last one is also platinum is also considered here. So we have this is the summarization of the table that summarizes all the reactions of metals with the oxygen, water, and also with the acid. So you can easily memorize this by using this table. It will be helpful for you for memorizing of the reactions of the metals, highly reactive metals which are present on the top, and the least reactive or unreactive metal that are present in the bottom of the reactivity series, and their reactions with these substances. Next, I have something for you. There is a mnemonic through which you can easily remember the reactivity series of the metals, and through these mnemonic you can remember the reactivity series which is from that starts from the potassium and ends at the gold, and also the platinum is also included here. So you can have some more mnemonics through which you can easily consider this, but I will also tell you one. You can also visualize the reactivity series as a staircase with the most reactive metal at the top and the least reactive metal at the bottom. So there are two mnemonics which I will share with you. We have, you can take this mnemonic to remember. You can take the first letter as the first metal, like we have P that represents the potassium, right? And then we have sodium. You can take the S from the stop as the sodium, and then calling calcium. So we have potassium, sodium, calcium, then me from M we have magnesium. You can just take the first letter. After the magnesium we have aluminum, and then we have zinc, we have I from the iron, and then we have lead, copper, silver, and then we have gold, and the last you can have the platinum. So this is the mnemonic through which you can easily remember the reactivity series. And one more mnemonic is this one. Please send cat, monkeys, and zebras and the lovely happy cages made of silver, gold, and platinum. So we have the P potassium, S sodium, C calcium, and magnesium, and then magnesium we have A that represents aluminum, and Z zinc, I from the iron, and after the iron we have L lead, and then lead you have C copper, then silver, gold, and platinum all. You can use these mnemonics to remember the reactivity series. So this is all about today. Hope you understand all. We are done with the chapter number 15, that is of the reactivity of the metals. If you have any question or if you have any query, you can ask in the comment box. Hope you understand all this. If you like the content, then please subscribe or like our channel. We will meet in the next video.